My name is Aruna Wanninayake. Today my presentation is using flip search to place limits on the scalars in the dark sector. First of all, I am going to give you a brief introduction about the dark matter. I know Kelly also gave some information about that. I am not going to talk that much. Dark matter is believed to exist from the gravitational effect on visible matter, and dark matter doesn't emit or scatter any radiomagnetic radiation, and they are non-luminous. Therefore, we can't see the dark matter. And also, composition-wise, we don't know the composition exactly, and majority of the universe is the dark matter. According to this picture, you can see the 74% is dark energy, 22% is dark matter. Only 12% is the visible matter. When we consider about how to detect dark matter, there are two main methods to detect dark matters. First one is direct detection method. Second one is indirect detection. In the direct detection method, we use the semiconductor detector. When the dark matter particle hit with the semiconductor atoms, then it deposits the sufficient energy to make recoil events. We are going to calculate this number of these recoil events in order to set the dark matter. CDMS, CREST, Eureka, Septic are some experiments use the direct detection method. Most of these experiments are done in underground laboratories to prevent the cosmic microwave background. When we consider the indirect detection method, the basic idea behind the indirect detection method, when the dark matter particle hit with each other, it annihilates giving off some detectable byproduct. Examples: gamma rays, neutrinos, and antimatter. We are going to detect those byproducts in order to find the dark matter in the indirect detection. Fermi, gamma ray, telescope, deep red family are some example experiments use indirect detection. When we consider about the thermal wind, they remain attractive candidate for the dark matter because they give the appropriate relic abundance, and they are very promising in terms of the direct and indirect detection because they have quick connection to the standard model particles. As I explained earlier in the previous slide, if the dark matter annihilates to some standard model particle state, cosmic ray detectors can detect them. Then it has some connection to the relic abundance. Then according to this data, we can find the relic abundance using this equation. Now I am going to explain some experiments use the how dark matter search. First one is the familia. In this experiment, data indicate sharp increment of the positron fraction. This result confirms the dark matter annihilation into positrons and electrons. In this case, it requires a large cross section. In the AT experiment, it is also a cosmic ray detector. This also can study electrons and positrons. WMAP experiment, we can explain in the WMAP experiment data can be explained synchrotron radiation from the electron and positron produced from the dark matter annihilation in the galactic center. In the Ecret gamma ray measurement in the galactic center provide hint of the excess at the 10 to 50 gigaelectron volt. According to these data, we can we can conclude that there is some electronic production in the galaxies. And also high energy positron can be produced through the annihilation process. When we consider in the high energy electrons and positron, when we model the dark matter, we have to face some challenges. When the familiar and erratic signals require a much larger cross section, but it doesn't allow by the thermocratic abundance. In the typical annihilation via the Z boson gives the very low hard leptons, and annihilation into the W bosons produce some hard leptons. But many more soft leptons produced through the hadronic shower. Other thing is, even if a high annihilation rate into lepton, annihilation rate into hadronic mode must be very low. All these issues can be addressed by the new force in dark sector. When we consider about the new force in dark sector, there is a big important thing is enhancements of the annihilation cross section. The new force carrier can distort the wave function of the incoming particle, and it gives the significant enhancement of the annihilation cross section. The second important thing is with the new force carrier, it's open up a new annihilation channel. It is the main annihilation channel. In this situation, even with a smaller interaction with the Standard Model particle, can lead them into decay into the Standard Model states. If they decay into leptons, then hard spectrum of the positron can be arise naturally. When we consider how to understand this new force, the Summerfield theory can be used. In the Summerfield theory, it explains how the annihilation cross section is going arise. Using this example, I can show you first neglecting the cross section of neglecting the gravity, the cross section of the particle hit with the star and absorb with the star. Is pi r square. Here r is the radius of the star. But considering gravity, the cross section will be 5 V max square. Then we can calculate the V max square using the energy conservation and the angular momentum. Then we can see the cross section like this equation. According to this equation, you can see with the very low particle velocity, cross section will be very high. When we consider the Summerfield enhancement more quantitatively, the particle interacting via, we can consider the particles interacting via potential. If we assume the dark matter coupling to mediator with coupling constant lambda, and wave function can be written as this equation. This is like this is okay with the Schrödinger equation. Here the potential is like the Yukawa type potential. Then Summerfield enhancement can be written using this equation. Now we can solve the Schrödinger equation using the boundary condition, and we can take the Sommerfield enhancement like this. And now if we define the dimensionless parameters, and then we can write the Sommerfield enhancement is equal to this equation. Here the important things we can see, even in this case, we can see the Sommerfield enhancement saturate the low velocity particles, and the specific value for the epsilon phi, the Yukawa potential develop threshold boundary states. When we see how this force, this new force arise, it must have a light force carrier. Other thing is massless particles are disfavored by the agreement between the Big Bang nucleus size and the primordial light measurement. Therefore, there must be massive degree of freedom. There are three major candidates for that. Coupled to a light scalar field, which is theorized to an attractive attraction, Goldstein-like derivative coupling to a matter, and coupling to a spring 1 gauge field. As the conclusion, there could be a new force in the dark sector. Sommerfield has explained this mechanism of the enhancement of the annihilation cross-section. This view, the new force can improve the annihilation cross-section in the dark sector for low velocity particles. These are my references. Acknowledgement to the Dr. Astroparticle.